On this episode, trees, bioretention, and the opportunities for them to fix clogging problems. Hey everyone, and welcome back to Ideanthro, and welcome back to the fourth video. This mini-series is getting quite long. The fourth video in this mini-series looking at trees and bioretention systems and all sorts of stuff associated with that. This came about because of episode 93, where we looked at trees and bioretention systems in a little bit of detail. But in this episode, we are also relating back to episode 98, where we looked at a relatively young bioretention system that had become clogged up with sediment from house building sites, most likely. And in that video, we looked at that and how to investigate that. But what it has also reminded me is I have some thoughts and some ideas about, I think, an idea of how we could potentially rehabilitate that system with really well thought out planting. So, bear with me here. Let's try and explain this. The first thing that I want to say though is that particular system in episode 98 was a relatively new system, and it had clogged up, most likely, from sediment from house building sites. And the stage that that system is at is that the contractor needs to get it working and draining properly in order to then hand over to council. The solution that I'm going to talk about in this video, I do not believe is an appropriate solution for that situation. Because in that situation, the system is new and council should be receiving a system that is in brand new or very, very, very close to brand new condition. This solution is more about how to take a clogged bioretention system, and it could look like that one in episode 98. And if you want to use that as context for thinking about this, then by all means go and look at that video so you've got that context. This is a solution that I think is more appropriate if you are a local government who owns some bioretention systems and one or more of those are clogged up and you need a cost-effective way to get those draining again without digging the system up and starting again. Because digging the system up and starting again is essentially, not quite, but essentially as expensive as building it in the first place. So, I am going to tell you a story now about a bioretention system that I was involved with when I worked at Logan City Council. This was the 3rd Avenue bioretention system. And this particular system attracted a fair bit of attention in council because it wasn't the most attractive system. It got a lot of sediment in it from house building sites. It clogged up. It then grew a whole bunch of aquatic weeds like typha in it. And what's more, it was on a relatively main boulevard, relatively near to the council office. So not only did all the council staff see it, not only did the residents see it, but the councillors saw it as well. It was quite famous. And this particular system, so it clogged up before it came to be handed over to council. And in this particular situation, it was clogged up and it came for that site to go off maintenance, for the asset to come across to council. And because of a whole bunch of other stuff that went on, which I can't actually remember a lot of the details of, and it's not relevant to the story, it came to be that council called up the bonds. So for anyone who's not familiar with how the handover process works, developer builds asset, developer must maintain asset for a period of time before handing to council to prove that the asset works. During that period of time, councils hold typically a 5% maintenance security bond across the entire development. And that is security to make sure that if stuff doesn't go right, they have a little bit of a lever, a little bit of a stick to hold over that developer such that either they fix it or B, council call up the bonds and take that money so that council can fix that problem. So it's security for council to make sure that ultimately the subdivision gets done the way it should. And we're back. Sorry about that slight glitch. You can tell this mini-series has got long when we just used up all the storage on the camera. But back to the story. So, council called up the bonds on this particular development for reasons not related to the bioretention system primarily, but the bioretention system did have problems. So at the end of that, the department within which I worked ended up with a small sum of money. It was about $9,000, if I remember correctly, to ostensibly rehab this clogged up bioretention system. The problem here was the conventional wisdom, which would be dig it out and start again, wasn't going to cut it in that particular instance because of the size of the system. Starting again and rebuilding it would have cost something like $30,000. We didn't have that. We got something like 9 out of this process. So we had to think up an option for how to rehab that particular system, and get it to at least a semi-functional state without blowing the budget. So here's what we did. At the time, we knew of some research that had come out of, again, Monash University from lab scale testing. I'm pretty certain. I don't think it came from field testing. It could have come from both, but lab scale testing for sure, which showed 2 interesting things. One of which, that some species of bioretention system, some species of plant that are used in bioretention system, are particularly good at keeping the filter media draining freely. Species like Carex and species like Melaleucas here are particularly good at keeping the filter media draining because they have this vigorous and constant root growth that breaks up the filter media, creates space for water to flow through the system, even if over time there's sediment coming in and starting to kind of compact that and starting to, possibly block it up. These species are particularly good at keeping them open. The second thing was that there was research that showed that on new systems, really often you built them with, the theoretical 200 mils per hour of hydraulic conductivity of water getting through the filter media. You built them with that, and regardless of what happened, even if things were done perfectly, they lose a lot of that hydraulic conductivity really early on and drop down to 50 mils an hour or less, essentially regardless of what happens. And then if you have a system that isn't badly damaged with sediment and does have good plant species in it, as those plants establish, the hydraulic conductivity re-establishes and can go back and approach or even exceed the initial hydraulic conductivity. So with those 2 things in mind, we went, okay, we are going to try and use some really, really well thought out planting of species. Before I forget, I need to recognize, I remember that at the time that I did this, I gave a call to Jace Sonneman at Designflow, and he gave me some thoughts about the species that I subsequently used here. So thank you, Jace, because that was a freebie. Thank you for doing that. Back on with the story. So we decided to use some really well thought out planting to try and re-establish the hydraulic conductivity of this system without having to remove any of the sediment. So at this point, this system had like an inch. I think I can show you a photo of this point of my car keys with the sediment next to it. Like an inch of really thick, really goopy sediment on the surface that had blocked it up. And it had typha in it, and it was ponding water. And we did several things to try and get this draining again. Firstly, we removed the caps on the flush out points of the system to drain it back down, right? We needed to get the water out of it. Secondly, I had a contractor come in and they hand pulled all the weeds and all the typha from the system. A big thank you to the crew at Active Eco for doing that. That's quite a bit of manual work to do that as it happens. So thank you. They hand pulled all of those typha. There was one stand of really good juncus in the system. They left that there because, we knew it was doing well. We then went and dug a hole in the filter media, right down to the drainage layer, and placed a PVC pipe in it. And we left that PVC pipe roughly 100 mils. The top of it was roughly 100 mils above the top of the surface, no cap on it. And we backfilled around it. So what that did was, that shortened the extended detention depth. Oh, that's something I didn't mention here. The extended detention depth in this system was built too deep. It was at 500 or 600 mils when it should have been at 300 or less. So we knew that if we have a system that's like badly clogged up and the extended detention depth is too deep, odds are, like if we let this rain in this system as it is again, it's just going to fill up and drown out any plants that we put in. So we used this PVC pipe to shorten the extended detention depth back really short, back to 100 mils deep. We backfilled around it, so what would happen is water could flow down into that PVC pipe, flow down into the gravel drainage layer, out into the gravel. We didn't connect it to the under drainage pipes. The water went back into the gravel, then back into the under drainage pipes. Anyway, the point is we shortened the extended detention depth. If we'd had a better designed pit, I would have just cut a hole in the side of the pit. We shortened the extended detention, the weeds were hand pulled, and then we came back in and planted a mix of species, some of which were far wetter, more wetland species, more aquatic emergent wetland species than you would normally see in a bioretention system, through to plants that were typical bioretention species plants, but were at the wetter end of what you would normally see. So that's plants like Carex and like Juncus. So we had this mix here. And what we were doing was we were hedging our bets that if what we had in mind here, which is by establishing the right plants in the system, particularly the Carex, which is known with its vigorous root growth to be able to break systems, break the filter media open and keep them draining, we're hedging our bets. If things went right, these plants would do well and they would open back up the filter media and we'd get the thing draining again. And in that instance, the plants that were on the bioretention, the wetter end of the bioretention spectrum, would survive and the wetland plants would die. But if things didn't go right, then what would happen is the system would clog up again and we'd have some wetland plants in here that could handle that excessively wet condition, and we'd essentially have transitioned the system to a wetland. So we hedged our bets. Well, what happened? The contractor came in, they planted the plants, and then I came out before the next rainfall event and I saw it, and the system drained really quickly. And we're like, okay, this is a positive. Now we've short-circuited a lot of the extended detention, but even that last 100 mils drained away far quicker than I'd ever seen in this system before. And the reason we think for that was that the hand pulling, the mechanical removal of the typha had broken up the sediment layer on the surface initially. So we'd restored mechanically a bit of the hydraulic conductivity. I was like, okay, this is useful, this is positive, we're on the right track, but it doesn't prove anything yet. And then subsequently over the next kind of 4 weeks or so, I kept looking at the system every time it drained, and it started to slow down. It stopped draining as quickly as it had been in that first rainfall event, and I was like, oops, the experiment hasn't worked. And we're like, okay, but that's okay. We've hedged our bets here. This is going to transition to a wetland. And then something amazing happened. Over that summer, because the works were done in like early November, and summer is the growing season. It's the wet season and the growing season for us. Over that summer, the plants took off like I have never seen before in a bioretention system. I'll show you a photo here of the system not long after planting. And then this next photo is a photograph of the system. It's either 3 or 6 months later. I'll pop that up on the screen to tell you which that is. And the plants absolutely took off. And you know what? The system kept draining. Now, I'm not saying it kept draining fast, and I never got an exact hydraulic conductivity measurement of this system, but it did keep draining. And we re-established a system that, admittedly, had a shorter extended detention depth, but was functional to some degree as a bioretention system and looked way more attractive than that system did when it had all the weeds in it. And bear in mind, you've just seen a couple of photos of this, right? There's a house immediately on either side of this, looking into this hole in the ground that's also a detention basin. The depth is the detention basin. Ugh. Anyway, it's not a good looking system. And so it re-established that hydraulic conductivity. And then it maintained it over quite a number of years. Unfortunately, over time, if you go visit that system now, you will find that it no longer has any vegetation in it. And that is because at some point the maintenance contract stopped, the weeds overran it, I believe there was a public complaint, and then the system was slashed. Oops. Unfortunately, my lovely case study can't be looked at anymore. But the point is that we have a kind of an initial potential proof of concept here. So where does this tie back to trees? Well, what we also know here, I think there's a crow that's about to go and attack our bag of camera gear and everything. Yep, it's looking awfully interested in it. Anyway, it won't do any harm. Maybe. If it does do any harm, I'm going to run out of shot in just a second. Boy, it's really... Spin around to capture this, Ben. See, there is Mr. Crow having a... thank you, car, for scaring it away. Back to the video. So trees. Where I see potential is the lab scale testing that Monash Uni did here showed that the Carex that I used in that particular system, pretty good for re-establishing hydraulic conductivity, but Melaleucas were also really good at it. Now, they haven't tested a super wide variety of species. So in fact, it's possible that there are many species that are good at restoring hydraulic conductivity, but Melaleucas are one of them. And we know from Hoyland Street, where we are today, that Melaleucas grow really well in bioretention. So I could see a situation, coming back to the system in episode 98, for a system like that, where it's clogged up. If I was a council and needed to try and re-establish the hydraulic conductivity in that system without rebuilding it, here's what I'd do today. I would go and remove the caps on the flush out points of the system, because that reduces the extended detention depth. Or you could punch a new hole in the side of the pit. You need to do something to reduce the extended detention depth to make sure make sure the system can't pond huge amounts of water for long periods of time that are going to kill terrestrial plants. I would then come in and plant a bucket load of Melaleuca, probably a bucket load of Carex as well, a mix of other species to hedge our bets either way, just like we did at 3rd Avenue. And then I would put in the effort into getting those plants established, because my experience suggests to me, I cannot prove this. This is not without risks, this idea. This is, I said it then, it's an idea. It is not a proven approach. It's an idea with one particularly useful case study demonstrating it. But my idea here is that I would come in, plant bucket loads of Melaleuca, bucket loads of Carex, a whole mix of other species as well, and then put my effort into re-establishing those, because I think they would be able to re-establish the hydraulic conductivity of the system. At some point then in the future, I would test the hydraulic conductivity, and then if it was flowing relatively well, at that point I would close the flush out points on the system and send it back to working like a bioretention system with 300 mils of extended detention depth. And I reckon you could get a functional system back out of that without having to rebuild it. Okay, what do you think of that idea? I'm really curious to know. If you've got any comments, got any questions, by all means, hit us up on YouTube, Facebook, or on the Ideanthro website. But until next time, where we're back for video 5 in this trees and bioretention system series, I really hope you're interested by this, because by episode 5, we're into week 3 of this. We'll be back for episode 5 and talking about more of trees and bioretention. Thanks for tuning in. We'll see you then.